Hi students, have a nice day. In the last section we have seen that the ionization enthalpy. In this section we are going to discuss about the factors affecting the ionization enthalpy and the variation of ionization enthalpy across the period and in the group. As we know that ionization enthalpy is the energy or enthalpy required to remove loosely held or loosely bound electron from an isolated gaseous atom. Okay, what is ionization enthalpy? The energy required to remove the electron from the valence shell, that is loosely held electron, from an isolated gaseous atom. Okay, that is ionization enthalpy. And in the case of lithium, it is 520 kilojoule. Lithium loses one electron, it is 520. Then we try to remove one more electron from the unipositive ion. The ionization enthalpy is called the second ionization enthalpy. And when we try to remove one more electron from the dipositive ion or cation, it is called the third ionization enthalpy. The successive ionization enthalpies are always increases, and remember that the ionization enthalpy is always positive because it is energy required. Okay, and delta IH3 is greater than delta IH2 is greater than delta IH1. All these things we discussed in the last section. So today we are going to discuss about the factors affecting the ionization enthalpy. Okay, factors affecting the ionization enthalpy. Our first factor is size of the atom or atomic size. Okay, second factor is magnitude of nuclear charge, or simply we can say that nuclear charge. Third factor is the screening effect or shielding effect. Screening effect or shielding effect is the third factor. And the fourth factor which affecting the ionization enthalpy is penetration effect. Okay, I think you heard of a new word, penetration effect. And finally, the factor affecting ionization enthalpy is electronic configuration. Okay, stable electronic configuration or simply electronic configuration. Let's discuss one by one. Okay, let us discuss one by one. First is atomic size. When size increases, the attraction between the nucleus and valence shell electron decreases, and consequently the ionization enthalpy decreases. Okay, for example, lithium. In the case of lithium, the ionization enthalpy is 520 kilojoule. Lithium plus 1 electron. Remember that the ion is in gaseous state. Okay, lithium plus. And the ionization enthalpy is equal to 520 kilojoule per mole. Okay. Ionization enthalpy usually expressed in kilojoule per mole, also in electron volt. And in the case of sodium, Na gas gives Na plus gas plus 1 electron. The ionization enthalpy is equal to 495 kilojoule per mole. Okay, what about the ionization enthalpy of sodium? It is 495, or in some other textbook 96, no problem. 495 kilojoule per mole. And in the case of potassium, okay, potassium gas gives potassium gaseous ion plus 1 electron. The ionization enthalpy is equal to 419 kilojoule per mole. Okay, 419 kilojoule per mole. So what do you understand from this data? When size increases, lithium the valence shell electronic configuration. In the case of lithium, 1s2, 2s1. In the case of sodium, 1s2, 2s2, 2p6, 3s1. Okay. In the case of potassium, it is argon. Up to argon 18 electron is completely filled in the inner shell and 4s1. What it means? The electron is added to successive shells. So size increases, ionization enthalpy decreases. That's a very important thing. Size of the atom increases, ionization enthalpy decreases. Okay, remember that. And the second factor is, so first factor is size or atomic size or simply size of the atom. And second factor is magnitude of nuclear charge. Magnitude of nuclear charge. Nuclear charge. Magnitude of the nuclear charge. When the nuclear charge increases, the attraction between the nucleus and the valence shell electron increases. Okay, the nucleus are strongly or firmly held the valence shell electron. And what happens? The ionization enthalpy increases. So remember that when the nuclear charge increases, the ionization enthalpy increases because of when nuclear charge increases, the attraction between the nucleus and the electron increases and the nucleus strongly held the electron and we supply more energy to remove that electrons. Okay. Size increase nucleus valence shell attraction decrease ionization enthalpy decrease. Okay, size increases, nucleus valence shell attraction decrease and attraction decrease ionization energy decrease. But nuclear charge in the case, if nuclear charge increases, the attraction between the nucleus and valence shell electron is increases and the nucleus strongly held or firmly held the valence shell electron and therefore the ionization enthalpy increases. Okay, lithium 520, beryllium is 899. Okay, 899. Beryllium is 899. Why? Okay, in the case of lithium, it is 520 kilojoule per mole. And in the case of beryllium, okay, 4, nuclear charge increases and the electron is added to the same shell. 1s2, 2s2. Okay, here 1s2, 2s1. Nuclear charge increases, the ionization enthalpy also increases. Ionization enthalpy increases by increasing the nuclear charge. Okay, the next is a screening or shielding effect. What is screening or shielding? In the case of multi-electron, we already discussed in the second chapter, in the case of multi-electrons, the inner electron screens or shield the valence shell electron from the attraction of the nucleus. Okay, inner electron screens or shield the valence shell electron from the attraction of the nucleus. Okay, valence shell electron inner shell electron screen cheyum. Nucleus in attraction on screen cheyum. Okay, appo nucleus valence shell effectively hold cheyamatadu. Okay, the nucleus couldn't hold the valence shell electron effectively. So what happens? Attraction between the nucleus and the electron decreases and ionization enthalpy decreases. Okay, nucleus electron attraction decrease ionization energy decrease. Remember that. Okay, so screening effect increases, ionization enthalpy decreases. What happens? Screening increases, when screening increases, the inner electrons, okay, the inner electron screens or shield the valential electron, and therefore the attraction between the nucleus and the valential electron decreasing, and thus ionization energy decreases. Screening increases, ionization energy decreases. Okay, and what about the screening order of the orbitals? Third point is screening or shielding. Okay, shielding effects. Screening effect or shielding. What is the order of screening effect? S screens more than the P, than the D, and than the F. So which orbital screens more effectively? S orbital. Okay, S orbital screens more effectively than the P orbital, than the D orbital, than the F orbital. Okay, so screening effect or shielding effect increases, ionization enthalpy decreases. And the next point is penetrating effect or penetration. Okay, penetration effect. What is penetration? Okay, as we know that the inner electron, in the case of multi-electron atom, the inner electron screens the valential electron. And in the case of S orbital, okay, let's take the S orbital. In the case of S orbital, the electron has, the probability of electron is more nearly the nucleus. Okay, the probability of electron being found to be near the nucleus. Electron, S orbital electron nucleus in the nucleus than the P electron, than the D electron, than the F electrons. So on the other side, or in another sensor, S electron has more penetration. Sorry, S electron has more penetration. So penetration increases. Okay, penetration increases, ionization energy increases. It is difficult to remove the S electron than the P electrons. Okay, it's a new term. Please note it. Penetration effect. Penetration effect means the electrons are more close to the nucleus, especially S electron. So S electron more close to the nucleus than the P electrons. That means S has more penetrating effects. Okay, more penetrating effect means the electron is more close to the nucleus. So what happens? If the electron is more close to the nucleus, it is very difficult, or it is difficult to remove the electron from this orbital. Okay, so the removal of electron from the S orbital is required more energy than the P orbital. And the penetration effect, okay, I write here, the fourth factor is penetration. Okay, penetrating or penetration effects. Say new effects. S orbital has more penetrating effect than the P, than the D, than the F orbital. Okay, than the F orbital. Are you clear? Yes. Then the removal of electron from the S orbital is difficult to that of the P orbital in a same shell. Okay. For example, for 2s electron and a 2p electron is there. 2s2, 2p2. Okay. The electronic configuration of the carbon atom. 1s2, 2s2, 2p2. Okay, S has more penetrating effect. That means S is more close to the nucleus than the P orbital. So which electron we can easily remove? P electrons. it is difficult, it is more energy required to remove the s electron. So that's about the penetration effect or penetrating effect. And the last one is electronic configuration. Okay, electronic configuration. Some elements have stable electronic configuration than the other elements. For example, in the case of nitrogen, the electronic configuration is stable. Why? As you study, half-filled and completely filled orbitals are more stable than partially filled orbitals. Okay, half-filled and completely filled orbitals are more stable than partially filled orbitals. In the case of nitrogen, 1s2, 2s2, 2p3. Okay, 2p3. And in the case of oxygen, it is 1s2, 2s2, 2p4. Okay, so this is stable electronic configuration. That is a stable electronic configuration. Why it is stable electronic configuration? Because it has half-filled p orbitals. Half-filled p orbitals. Are you clear? And in the case of oxygen, it is less stable. Why it is less stable? It has partially filled p orbitals. There are 4 electrons, so 1 electron is paired. So this orbital is partially filled, less stable. Okay, that's why the ionization enthalpy is changing. In the case of nitrogen, it is 1403. Okay, and in the case of oxygen, it is 1300. 14. Okay, so in the case of nitrogen, the ionization enthalpy is 1400, 3 or 2 kilojoule per mole. In the case of oxygen, it is 1314 kilojoule per mole. So those elements, those atoms having stable electronic configuration, the ionization energy is higher. Okay, the ionization energy is higher. And those atoms with the less stable electronic configuration, their ionization energy is less. Okay, so we will discuss in the period and group. So these are the main factors. Okay, 5 factors affecting the ionization enthalpy. One is atomic size or size of the atom. Second one is nuclear charge or magnitude of the nuclear charge. Third one is screening effect or shielding effect. Fourth one is penetration effect. Okay, then fifth one is electronic configuration. Okay, next is the variation of ionization enthalpy across the period and in the group. First of all, we have to discuss about the variation of ionization enthalpy in the period. Let's take the second period. Okay, in any period the trend is same. First we try to take the second period. Okay, in the second period there are 8 elements. From left to right, ionization enthalpy increases. Generally, ionization enthalpy increases across the period. Okay, this is due to, from left to right, nuclear charge increases as well as the size of the atom decreases. As we already discussed, size increases, ionization enthalpy decreases. What about size decreases? When size decreases, ionization enthalpy increases. So two reasons. One is nuclear charge. Okay, magnitude of the nuclear charge. From left to right, nuclear charge increases. And the second reason is atomic size decreases from left to right. Okay, so here I draw a graph by plotting ionization enthalpy versus atomic number for second period. Lithium. Okay, lithium 520 kilojoule per mole. The energy is expressed in kilojoule. Beryllium 899 kilojoule. Boron. Okay, little less. We will discuss later. 801. Carbon 1086. Nitrogen 1402 or 403. Oxygen 1340. Fluorine 1681. And neon, the noble gas neon 2080. Okay, so generally the ionization enthalpy increases, but there are some irregularities. Okay, why this irregularity? It is due to electronic configuration. So first of all, we discuss about the variation in the period. Okay, in the period. I increases from left to right. From left to right. Okay, from L to R means left to right. Why? Because nuclear charge increases as well as atomic size decreases. Okay, beryllium. Beryllium 1s2, 2s2. And the ionization enthalpy delta IH is equal to 899. For boron, 1s2, 2s2, 2p1. Ionization enthalpy of boron is 801. Okay, that much kilojoule per mole. Kilojoule per mole. Kilojoule per mole. Why this irregularity? It is due to electronic configuration. Okay, as we already discussed. Beryllium has stable electronic configuration. Completely filled s orbital. Valence shell s orbital is completely filled. In the case of boron, the valence shell is partially filled. P orbital. There are 3 p orbital. One electron occupied in the p orbital. So it is easy to remove this p electron and it becomes b plus 1s2, 2s2. Now it is stable. Okay, the p electron in the boron atom is easily to remove as compared to the removal of 2s2 electron from the beryllium. That's why boron has little less ionization energy. The same anomaly, the same irregularity how to see in the case of nitrogen and oxygen. Okay, in the case of nitrogen, the electronic configuration is 1s2, 2s2, 2p3. Okay, as we already discussed. In the case of oxygen, 1s2, 2s2, 2p4. This is stable because of half-filled orbitals. Half-filled orbitals are more stable than partially filled. In the case of oxygen, the orbital is partially filled. Are you clear? It's a very important information. Half-filled and completely filled orbitals are more stable than partially filled. Here is completely filled. This one is partially filled. That's why ionization energy is lesser as compared to the beryllium. Usually the expected from left to right increases, but decreases due to electronic configuration. In similar way, nitrogen and oxygen. Nitrogen has 1402. Okay, 1402 kilojoule per mole. In the case of oxygen, it is 1314. Okay, it's also due to electronic configuration. So generally, from left to right, ionization enthalpy increases due to increase in the nuclear charge and a decrease in the atomic size. But there are some irregularities which is due to stable electronic configuration. Okay, then next we have to discuss about the variation of ionization enthalpy in the group. Okay, in the group ionization energy decreases. Okay, it's always decreases. Ionization enthalpy of elements in the group always decreases. Here I took the alkali metals, first group elements. Okay, first group elements. Lithium 520. Okay, ionization energy versus atomic number plots. Lithium 520, sodium 496 kilojoule, and potassium 490. Okay, this decrease is sharp. Then the decrease is the slope of the line is less. Rubidium 403. Okay, potassium 490, rubidium 403, and cesium 374 kilojoule per mole. Okay, so in group, if you take any group from top to bottom, ionization enthalpy decreases. It is due to increase in the size of the atom. From top to bottom, the size increases. Sodium is bigger than lithium, potassium is bigger than sodium, rubidium is bigger than potassium, cesium is bigger than rubidium. So when size increases, the attraction between the nucleus and valence shell electron decreases. Okay, once again, when size increases, the attraction between the nucleus and the valence shell decreases, and the electron is not firmly attracted, not strongly attracted by the nucleus, and consequently the ionization energy decreases. Okay, so that's about the ionization energy and the variation of ionization energy in a group and as well as across the image. Okay, these figures are in the NCERT book. You may please copy into your notebook. In the next section, we will discuss about the electron gain enthalpy and electronegativity. Thank you.